Hello students, today we will discuss about root-locus techniques for control system design. Using root-locus, we will study about the stability and the characteristics of transient response of a closed-loop systems and the locations of the closed-loop poles and the problems to solve characteristic equation, for example, difficult for a system of third or higher order and second one is tedious for varying parameters. So varying the loop gain K. If you look at this, we have uh, one system, closed loop system. The open loop gain K is an important parameter that can affect the performance of a system. So in many systems, simple gain adjustment may move the closed loop poles to desired locations. Then the design problem may become the selection of an appropriate gain value. So it is important to know how the closed loop poles move in the S-plane as the loop gain K is varied. So let's talk about root locus. The locus of the roots of the characteristic equation of the closed loop system as a specific parameter, usually gain K, is varied from 0 to infinity. The advantages of a root locus approach is number one, avoiding tedious and complex root solving calculations. Number two, clearly showing the contributions of each loop poles or zeros to the location of the closed loop poles. And number third is indicating the manner in which the loop poles and zeros should be modified so that the response meets system performance specifications. So let's start with an example. Consider a second order system shown in the figure below. So we have this closed loop system. Okay, we have input, we have output, and we have a open loop gain here, and we have a feedback. So closed loop transfer function of this given system is k over s square plus s plus k. And if we check the characteristic equation, which is s k plus s plus k is equals to 0, so roots of this characteristic equation is given here. So the roots of characteristic equation changes as the value of k changes. So when the k changes from 0 to infinity, how will the locus of the roots of the characteristic equation move? So we have the roots of the characteristic equation here, and now we will draw it on S-plane. So k is equals to 0, we have S1 is equals to 0 and S2 is equals to minus 1. So if we see, we have two poles, one is at 0 and another one is on minus 1. Okay, so we have 0 is less than k is less than 1 by 4. We will see as the value of k increases, the two negative real roots moves closer to each other. And if k is equals to 1 by 4, s1 is equals to s2 is equals to minus 1 by 2. Right? So if 1 over 4 is less than k is less than infinity, a pair of complex conjugate roots leaves the negative real axis and moves upward and downwards following the lines s is equals to minus 1 by 2. So if you look at that, we have some complex conjugate roots as well if the value of k increases or varies. So on the S-plane, using arrows to denote the direction of characteristic roots move when k is increases. So by numerical values to denote the gain at the poles. So by the root loci, we can analyze the system's behavior. Number one, stability. We can check when the root loci are on the left half plane, then the system is definitely stable for all the values of k which is greater than 0. And number 2 is steady state performance. There is an open loop pose at s is equals to 0. So the system is a type 1 system. And the steady state error is 0 under step input signal. So R over kV under ramp signal V naught t and infinity under the parabolic signal. So the number 3 is transient performance. There is a close relationship between root locus and the system behavior. On the real axis, k is less than 0.25. This is underdamped. If k is equals to 0.25, the system will be called as critically damped, and if k is greater than 0.25, then it will be called underdamped system. So however, it is difficult to draw root loci directly by closed loop characteristic roots solving methods. So the idea of the root loci: by loop transfer function, draw closed loop root loci directly. So now we'll check the relationship between zeros and poles of g of s into h of s and closed loop ones. So we have a system. So we check that the forward path will be equals to g of s. The feedback path is h of s. So the closed loop transfer function will be g of s over 1 plus g of s into h of s. So to draw the closed loop root locus is to solve the characteristic equation. So we have this 1 plus g of s into h of s is equals to 0. So that is the characteristic equation, and if we solve them further, we will have g of s into h of s is equals to minus 1. And this is called the root locus equation. Suppose that g of s into h of s has m zeros and n poles. The above equation can be written as g of s into h of s is equals to I is equals to 1 to m s minus zi over I is equals to 1 to n s minus pi, and this is equals to minus 1. So the value of the k varies from 0 to infinity. So we call this equation is a root loci equation. So since the h of s and g of s is a function of a complex variable s, the root locus equation can be described by the following two equations: magnitude equation and angle equation. So magnitude equation is related not only to zeros and poles of g of s into h of s, but also with the root locus gain. And the angle equation is only related to zeros and poles of g of s into h of s. So use AE to draw root loci and use ME to determine the value of k on root locus. So we'll have two equations: magnitude equation ME, and we use this for drawing the root loci, and the angle equation AE, which will be used to determine the value of k on root loci. So here we have an example. We have all the values here. So if we solve them further, we will check the poles of g of s into h of s. Here we have p1 is equals to 0, p2 is equals to minus 1 by t1, and p3 and 4 is equals to minus zeta omega n plus minus j omega d. And if we talk about the zeros of g of s into h of s, we have 0 as minus 1 over tau. Okay, so we have here, you can see in the figure given below, the poles and zeros of the given equation, example number 1. So for a point S1 on the root loci, we will use the AE equation, angle equation. So if we use that, we will have the angle for each of the vector drawn in the figure. So angle is in the direction of anti-clockwise, and we use ME, magnitude equation. So now we have example number 2. We have a unity feedback transfer function, which is g of s is equals to k over s. So one pole of g of s into h of s is equals to p1 is equals to 0. No, in this equation we have no zeros. Test a point s1 on the negative real axis. So we have seen that it is not. So all the points on the negative real axis are on root locus. The test a point outside the negative real axis s2 is equals to minus 1 into minus j. So we have the angle, which is 135 degrees. So all the points outside the negative real axis are not on the root locus. So probe by each point. Find all the points that satisfy the angle equation and on the s plane, and the link all these points into a smooth curve. Thus we have the system root locus when k changes from 0 to infinity. So number 2 is, as for the given k, find the points that satisfy the magnitude equation on the root locus. Then these points are required closed loop poles. However, it is unrealistic to apply such probe by each point method. So W.R. Evans in 1948 proposed a set of root loci drawing rules which simplify our